So thanks everybody for joining our RIG sensor mixer today. It's good to see so many colleagues together. So this will be like extremely fast introduction of what we do. So I call it soft electronics for mobile health and human-centered robotics. The motivation is really because of this Industry 4.0 or the fourth industrial revolution we are currently going through as a human society. It is called cyber physical systems, which includes Internet of Things, robotics, big data, artificial intelligence, and so on. I would personally like to call it cyber physical biosystems because I hope our human can still play a role. So examples include this wearable technology, which is growing really fast, and people are building all kinds of wearable health or performance tracking devices or communication devices. Another area is robotics, and particularly I'm interested in human-centered robots, such as processes or augmented capabilities, or even in the future, human-aware and human-centered robotics for social or medical care purposes. So ultimately, I think Elon Musk said it very well. Humans must merge with machines or become irrelevant in the AI age. But if you look at conventional machines, which are digital, rigid, but our body is completely analog and soft. So if you think of a conventional machine which has more than thousands of sensors, our human body is like a soft machine which rarely have sensors on us. But both systems are radiating highly personal, continuous, distributed, and multimodal data about our health, readiness, or performance, intention, emotion, specifically for humans. Conventional devices are rigid, bulky, monomodal, and short-term. Our group is spending the past 10 years building a skin-soft, hair-thin, multimodal, and long-term wearable electronic tattoos. Essentially, we use this kind of two-dimensional springs, which we call serpentine ribbons, to transform any kind of materials from rigid, stiff state to soft and stretchable state. It can be silicon, metal, or polymer. And we developed a very rapid prototyping technology called cut and paste method, literally cutting and pasting our circuit onto stretchable framework using this serpentine design. It is completely dry and just 10-minute process. You can cut and paste multiple times to incorporate multiple materials and sensors onto the same platform. This is a cut and pasted chest e-tattoo with gold electrodes measuring electrocardiogram and a piezo membrane measuring seismocardiogram. And if you calibrate blood pressure versus the RAC interval, which is the systole, then the faster our heart contracts, the higher blood pressure we have. We can use this calibrated curve to extract blood pressure beat by beat. And this is cut and pasted graphene e-tattoo, which is a monolayer, single carbon atom thick graphene. It is very transparent, but still electrically conductive. It can achieve very good conformal contact with human skin. It can be transferred just like a temporary tattoo sticker the kids are playing with a little bit of water. Under optical microscope, you can see how thin and how transparent. It is imperceptible when you wear it around the human eyes or on the face, and we can use eyeball rotation to control a drone. So this is an imperceptible human-robot interface. To incorporate chips and accelerometers, we can upgrade to cast solder paste process, where we can do a soldering of all kinds of ICs. This is a multi-layer cast solder pasted e-tattoo that is completely wireless and mobile, and we can simultaneously measure electrocardiogram and seismocardiogram and extract blood pressure or even cardiac output. And we are using this platform to collaborate with data scientists and pneumonia doctors to develop a chest multimodal ETA2 that can measure things like skin temperature, electrocardiogram, PPG, which can be converted to oxygen saturation, chest motion that can monitor coughing and so on for progressive pneumonia sensing and tracking. So ultimately, we have to develop the right ETA2 to be placed at the right location to measure the right thing. It can be highly multimodal and they can be fused to look into different things like fatigue or focus or physical stress or mental stress. In addition to e-tattoos, we're also starting to look into e-skins. E-tattoos are for human to wear for biometric sensing. E-skins are for robot to wear for human mimetic sensation. It's a very popular and busy field. And our specific contribution comes to this enhanced sensing sensitivity over a wide pressure range due to this kind of a hybrid response, piezo resistive and piezo capacitive response pressure sensor. And you can see we can enhance the sensitivity, especially at large pressure range. This can be a very sensitive e-skin that can directly measure the human pulse wave. This is still like an ETA2 use, but we can also mount it on a inflatable robotic finger. During inflation, you can see the capacitance barely changes because of our intrinsic decoupling between stretching and the pressure. Once it's in contact, you can see the pixels immediately shoot up with the capacitance information. And one of the pixels that's really palpating our pulse can give the pulse wave again. So this kind of stretchable e-skin can find a lot of future applications in software robotics and even human monitoring. So ultimately, I think the future is to close the loop for both ETA2 and e-skin. For ETA2, we want to do sensing, processing, analysis, diagnosis, and treatment running in the background so that our patients can be treated even before they know they are ill. For the e-skin, the robot needs to sense. They also need to actuate and stimulate the human. The human needs to process and control the robot, and the robot can react according to human commands. So that's a very quick summary, and here are my senior collaborators all over the world. And a special thanks to my group and my sponsors. Thank you very much for your attention.